Space is not silent. It is filled with whispers we are only beginning to hear. In recent years, the deepest quiet has been broken by sudden, mysterious signals. These signals do not come from distant stars or neighboring planets. They come from strange, fast-moving visitors passing through our own solar system, interstellar asteroids and comets from other star systems. The first two we met were named Oumuamua and Borisov. These objects are more than just cosmic rocks. They might be sending us strange, unexplained signals that challenge everything we think we know about the universe. By the end of this journey, you will understand 25 of these bizarre cosmic messages and what they could mean for our place in the galaxy. We will explore why an object might speed up without a visible engine, what it means to find a chemical fingerprint from another world, and whether we might have already missed a signal from an alien probe. This is a detective story written in light, motion, and silence. What do you believe is waiting for us in the dark between the stars? The first signal was not a sound or a flash of light, but a silent deviation in the dark. It came from our first known interstellar visitor, the object we call Oumuamua. As this strange, tumbling rock hurtled away from the sun after its brief encounter, astronomers tracking its path noticed something deeply puzzling. Its speed was changing in a way that pure gravity could not explain. According to every calculation based on the sun's pull and the planets it passed, Oumuamua should have been moving just a little bit slower. Instead, it was accelerating as if given an extra, invisible push. This was the Oumuamua acceleration anomaly, a tiny but undeniable signal written in the object's motion. It was the universe presenting us with a cosmic riddle. The immediate, most natural explanation was outgassing. Think of a comet which heats up as it nears the sun, releasing jets of gas and dust from its surface that act like tiny thrusters, subtly altering its course. But Oumuamua showed no visible coma, no tail of gas or dust that our telescopes could detect. It looked like a barren, inert asteroid, yet it was behaving like an active comet. This contradiction sent scientists scrambling. One compelling theory suggests it could have been outgassing hydrogen. A block of solid hydrogen ice warmed by the sun would release pure hydrogen gas. This gas is invisible to our telescopes, and its release could provide the precise push needed to explain the acceleration, all while leaving no visible trace. It is an elegant solution that fits within the laws of known physics. Yet, the absence of that visible tail opened the door to more speculative and far more thrilling possibilities. Could the push have come from something else entirely? The shape of Oumuamua, inferred from its wild brightness changes, suggested an object that was highly elongated, perhaps 10 times longer than it was wide. Some researchers, most notably Harvard's Avi Loeb, proposed that such a shape and its sunlight-driven acceleration were consistent with a concept we ourselves are developing, a light sail. A light sail is a thin, reflective sheet that uses the gentle pressure of sunlight for propulsion, needing no fuel. The idea was breathtaking, a suggestion that our first interstellar visitor might not be a natural rock, but a piece of discarded technology, a derelict probe from a distant civilization. This hypothesis led to a direct search for a more conventional signal. The Breakthrough Listen project aimed its powerful radio telescopes at Oumuamua, listening intently for any artificial transmissions, any hint of an active beacon or system. They heard nothing, only the profound silence of space. This radio silence, this non-signal, is itself a critical piece of the mystery. It does not rule out an artificial origin, but it deepens the puzzle. If it was a probe, it was long dead, a silent artifact tumbling through the void. If it was a natural hydrogen iceberg, it was a type of object we have never seen before. The acceleration anomaly stands as signal number one, a quiet nudge against our expectations that forced us to look at the cosmos with new and more uncertain eyes. While Oumuamua's mystery was one of motion, our second interstellar visitor offered a puzzle written in pure light. Comet 2I Borisov arrived just 2 years later, a more familiar sight with its brilliant tail of gas and dust. Astronomers did not just watch it pass, they dissected its light using a technique called spectroscopy to read its chemical signature. The signal they found was astonishing. Borisov was not just from another star, it was a perfectly preserved relic. Its composition was incredibly pristine, almost untouched since its formation in its own alien cradle. This chemical fingerprint was signal number 2, a direct message about the conditions in a planetary system we will never see. For scientists, this was like finding a perfectly sealed time capsule from another world. In our own solar system, comets are cosmic agitators. They spend most of their lives in the deep freeze of the outer solar system, but their orbits often bring them swinging in close to the sun, where solar heating cooks their surfaces, altering their original chemistry. Borisov showed no such signs of solar processing. Its light revealed it was profoundly primitive, suggesting it had lived a quiet, cold life in the outer reaches of its home system before being flung toward us. But the surprise grew deeper. Detailed analysis showed a glaring absence, a silence where scientists expected to find a specific signal. Borisov's coma, the cloud of gas around its nucleus, was missing carbon monoxide at the levels we see in most solar system comets. Carbon monoxide is a common volatile, a lightweight gas that easily boils off a comet's surface. Its scarcity in Borisov was a loud and clear clue. It tells us that the environment where this comet was born was chemically distinct from our own solar nebula. Perhaps its home star was cooler or hotter. Maybe the disk of material around that star had a different mix of ingredients from the very beginning. This single chemical signature forces us to confront a humbling truth. Our solar system, with its specific recipe for planets and comets, is not the universal standard. It is merely one example. Borisov is a direct sample proving that other star systems cook with different spices, following recipes that can produce objects fundamentally unlike anything in our own celestial backyard. So, while Oumuamua made us question what an object could be, Borisov asked us to reconsider where everything comes from. Its pristine light carried a signal of profound cosmic diversity, whispering that the galaxy is far stranger and more varied than we ever imagined. The silence from Oumuamua was broken by a claim that sent shockwaves through the astronomy community, not by a major observatory but from the realm of dedicated amateurs. Signal number 3 is the hypothetical Oumuamua radio burst, a whisper of a transmission that may or may not have ever happened. Shortly after the object's discovery, a small group of amateur radio astronomers reported picking up a brief, incredibly narrowband radio signal that seemed to originate from the object's direction. This was not the broad static of cosmic noise, but a sharp spike on a very specific frequency, the kind of signature often associated with artificial transmitters. The implications were staggering. If verified, it would have been the first direct, intentional-seeming signal from an interstellar object. The controversy erupted immediately. In professional science, a single, unverified observation from a non-peer-reviewed source is treated with extreme caution. The protocols are strict for a reason. Extraordinary claims require extraordinary evidence, and this evidence was fleeting and captured by equipment not under the constant calibration of a major institution. The signal was brief, and Oumuamua was moving fast, making it nearly impossible for other teams to point their dishes and confirm the finding before the moment was lost. What would such a signal imply if it were real? It would transform Oumuamua from a puzzling natural object into a potential artifact. A narrowband burst could be a beacon, a simple ping saying "I am here," or it could be leakage from an internal power source like the faint radio hum from a sleeping spacecraft. It would suggest not just a strange shape or odd motion, but an active or recently active piece of technology. the scientific community remains deeply skeptical, and rightly so. The history of astronomy is littered with exciting signals that turned out to be terrestrial interference, a passing satellite, or even a malfunctioning microwave oven. Yet beneath that skepticism lies a persistent intrigue. The very fact that it was reported and that it fits a tantalizing narrative keeps the idea alive in the corners of the conversation. It highlights a fundamental tension in the search for cosmic mysteries. Sometimes the most thrilling clues come from the edges of established science, from passionate observers outside the mainstream, presenting us with a ghost of a signal that is impossible to prove and equally impossible to completely forget. This struggle to interpret whispers led to a far more concrete, yet equally baffling signal. While Oumuamua's acceleration was a subtle push, its light curve was a shout. Every object in space reflects sunlight, and as it rotates, that brightness changes. By meticulously tracking these flickers, astronomers can map an object's shape and spin. What they saw for Oumuamua defied all expectations. Its brightness didn't just vary, it swung wildly by a factor of 10. This extreme fluctuation meant only one thing. Oumuamua was not a roughly spherical rock. It was tumbling through space in a state of non-principal axis rotation, a chaotic end-over-end spin, and its shape had to be profoundly asymmetric to create such a dramatic light show. The numbers pointed to an object at least 10 times longer than it was wide. Some analyses even suggested a ratio closer to 40:1, a shape more like a cosmic cigar or a flat, thin pancake tumbling through the void. This was signal number 4, a message written in flickering sunlight that screamed, "I am not normal." In our solar system, we see nothing like it. Typical asteroids are lumpy potatoes. Comets are dirty snowballs, often irregular but never to this extreme. So what natural process could forge such a bizarre form? One leading theory is tidal disruption. Picture a comet or asteroid from another system venturing too close to its home star. The star's immense gravity could stretch and tear the object apart, spinning it rapidly and shattering it into long, thin shards. Oumuamua could be one such splinter, a cosmic fragment flung from a violent stellar encounter. Another possibility is that it is a fractal-like aggregate of dust, a fragile structure built from tiny particles that somehow clumped together in a specific, elongated way. Yet the very extremeness of the shape pushes the imagination. Could a natural process really create something so perfectly, improbably slender and survive an interstellar journey? This physical enigma is why the light curve is such a powerful signal. It is not an ambiguous radio whisper, but a direct measurement of the object's geometry. And that geometry is so unusual, it forces us to question the entire catalogue of natural shapes we have compiled from our own cosmic backyard. It suggests that the processes at work around other stars can produce artifacts that look, to our eyes, almost engineered. The light curve does not tell us what Oumuamua is, but it screams at us about everything it is not. It is a silhouette against the stars, a shape that fits no comfortable category, leaving us to wonder if we are looking at a new class of celestial object or the shadow of something far more profound. The most telling clue about Oumuamua was the one it refused to give. Every comet we have ever observed, when it gets close to the sun, puts on a spectacular show. Solar heat vaporizes the ice on its surface, launching plumes of gas and dust that stream out into space, forming a glowing halo called a coma, and often a magnificent, sweeping tail. This outgassing is a comet's signature, its way of announcing its presence. For Oumuamua, astronomers around the world trained their most powerful telescopes, from Hubble to ground-based observatories, searching desperately for this very signal. They looked for the faint glow of dust, the specific chemical fingerprints of gases like cyanogen or diatomic carbon in its light. The result was a profound and puzzling silence. They found nothing, no coma, no tail, not even a hint of the dusty envelope that should have surrounded an object accelerating away from the sun. This was signal number 5, the missing coma, and its absence created a paradox at the heart of the mystery. How could something be pushed by outgassing without showing any signs of outgassing? It was like seeing a boat speed across a lake, kicking up a wake but seeing no engine and no propeller. This contradiction forced scientists to think outside the box of conventional comets. One compelling theory points to hydrogen. Imagine an iceberg, but made not of water ice, but of solid molecular hydrogen. This is an exotic substance that could only form in the coldest, densest reaches of a molecular cloud, the birthplace of stars. If Oumuamua was a hydrogen iceberg, the sun's warmth would have caused it to sublimate, turning the solid hydrogen directly into an invisible gas. Pure hydrogen is extremely difficult to detect at those distances with our current instruments, and it would not drag dust grains with it to form a visible tail. The push would be real and powerful, but the process would be utterly stealthy, leaving no trace for our telescopes to see. Another candidate is nitrogen ice. We see vast plains of it on Pluto, a frigid, solid landscape. A chunk of nitrogen ice from the outskirts of an alien planetary system could behave similarly, releasing pure nitrogen gas as it heats up, another substance that wouldn't create the traditional dusty coma we associate with comets. These explanations are elegant because they stay within the realm of known physics, yet they describe objects we have never directly observed. They are hypothetical answers to a very real observation of absence. This missing signal, therefore, is not an empty void. It is a data point of immense power. It tells us that if Oumuamua is natural, it is made of materials or has a structure so different from anything in our solar system that it operates by a hidden set of rules. The silence of its passage speaks volumes about the diversity of cosmic chemistry, suggesting that the universe builds with an inventory of materials far stranger than our own local experience would suggest. Borisov's light held more than just an absence. It also contained bright, sharp peaks that astronomers could read like a cosmic grocery list. Signal number 6 was the clear and strong detection of cyanogen gas in the comet's coma. Now, cyanogen sounds terrifying, a compound famous in astronomy for sparking a public panic over a century ago when Earth passed through the tail of Halley's Comet, but in space it is utterly routine. It is a common building block in comets, a simple molecule of one carbon and one nitrogen atom bound together. Finding it in Borisov was expected, a sign that some chemistry is universal. The intrigue, however, lay in its proportion. The amount of cyanogen detected was unusually high compared to other common cometary gases like diatomic carbon. This specific ratio was a subtle signal, a slight deviation from our solar system's average recipe. It was another quiet hint that Borisov's home kitchen mixed its ingredients with a slightly different hand, producing a familiar flavor but in a distinct concentration. Then came the real enigma, signal number 7. Buried within the brilliant lines of known gases like cyanogen, astronomers spotted a few faint spectral fingerprints that did not match any compound in their vast databases. These were unassigned lines, whispers of light at specific wavelengths that corresponded to nothing we have ever seen in a lab or in space. A spectrum is a barcode, with each line representing a specific atom or molecule vibrating or emitting light. We have catalogued millions of these barcodes. To find a line we cannot read means one of three things. First, it could be an exotic molecule that simply doesn't form in the environments we have studied, a compound forged under alien pressures and temperatures. Second, it could be a known molecule in a highly unusual state, perhaps super excited or ionized in a way that shifts its spectral signature into unfamiliar territory. The third and most humbling possibility is that it is merely noise, an artifact of the incredibly sensitive instruments themselves, a ghost in the machine. Yet the very possibility that it is real is what captivates. Those faint, unreadable lines are the equivalent of finding a single, unknown word in a message otherwise written in a language we almost understand. They represent the edge of our knowledge, a direct signal that some of the universe's chemistry remains, for now, a mystery written in light we have seen but cannot yet decipher. The most direct way to solve a cosmic mystery is to reach out and touch it. While our telescopes read light and motion, radar can reveal an object's true physical nature, bouncing radio waves off its surface to map its shape, spin, and even composition. With Oumuamua and Borisov moving too fast for any earthly radar dish to track, we were left with only hypotheticals. But these what-if scenarios form our next set of signals, the echoes we wished we could have heard. Signal 8 is the hypothetical radar return showing a metallic composition. Imagine aiming a radar beam at the object and receiving back an echo of exceptional strength and clarity. A natural, rocky surface scatters radar waves in a messy, diffuse pattern. A smooth, dense metal surface, however, would reflect those waves back with a sharp, coherent ping, like a mirror compared to a rough stone wall. Such a return would be electrifying. While metallic asteroids exist in our own solar system, they are rare. A predominantly metallic interstellar object would suggest it originated from the core of a shattered planetesimal, a fragment of an alien world's heart blasted into the void by a cataclysmic collision. It would be a geological sample from a planet that never was, telling a story of violence in a system we have never seen. Signal 9 flips that idea entirely. Instead of a hard metallic ping, the radar might return a faint, confused echo indicating a highly porous, fluffy structure. Picture the difference between bouncing a ball off a solid wall versus throwing it into a giant snowdrift. The snowdrift absorbs the energy. A radar echo from an object with the density of candy floss or a fractal dust ball would be weak and complex, suggesting a structure held together by the faintest of forces, more a cloud of rubble than a solid rock. This would support theories that some interstellar objects are not monolithic boulders, but fragile aggregates, cosmic dust bunnies assembled in the quiet corners of protoplanetary disks. They would be the ghosts of planetary formation, so delicate that a close pass to a star might not just melt them, but completely dissolve them into a scattered haze. Then comes the most speculative echo of all, signal 10. This is the notion of a repeating, structured radar pattern. A natural, irregular tumbling object produces a chaotic, unpredictable echo. But what if the return showed a clear, repeating signature? A consistent flash every few seconds, or a pattern of peaks and valleys that mirrored the object's rotation with mathematical precision. Such a signal could imply a surface with regular, engineered geometry. Think of the corner reflectors we leave on the moon, designed to bounce laser light directly back to its source. A repeating radar echo might hint at flat panels, right angles, or other unnatural symmetries on the object's surface, features that nature almost never creates on its own. While this is the most extreme and least likely scenario, it represents the ultimate goal of such a measurement, to search for the fingerprint of design in the chaos of space. We lack the technology to chase these echoes for our first 2 visitors, but that is changing. Future missions are already being planned, spacecraft designed to lie in wait and intercept the next interstellar passerby. Their instruments will be ready to send out that radar pulse and listen, not just for the whisper of composition or structure, but for any unnatural rhythm in the reply. These hypothetical signals remind us that some of the most profound discoveries are not just about what we see, but about how we choose to reach out and ask the universe a direct question, waiting for the echo to return. The mystery of silent acceleration did not leave our solar system with Oumuamua. It stayed home. Astronomers have recently identified a strange new class of objects in near-Earth space they call dark comets. These are not visitors from other stars, but local residents, and they are behaving in a deeply familiar way. Like Oumuamua, they exhibit clear non-gravitational acceleration, a subtle push that alters their orbits, yet they show no visible coma or tail. This is Signal 11, a phenomenon that turns an interstellar oddity into a potential solar system pattern. We are finding that whatever force propelled Oumuamua might be at work right in our own cosmic backyard. These dark comets provide a crucial link, a second chance to decode a signal we missed the first time. Because they are closer and on repeating orbits, we can observe them again and again, testing our theories in real time. The leading explanation for their hidden thrust is water. Picture an asteroid, not a classic icy comet, but a rocky body that has collected water ice within its porous interior or beneath a dark, dusty crust. As it swings near the sun, that ice heats up and turns directly into vapor. The water vapor escapes through tiny cracks and pores, acting like microscopic rocket jets. Because the process is contained and the gas is pure water vapor, it does not drag enough dust into space to form a visible cloud. The acceleration is real and measurable, but the mechanism remains stealthy, hidden from our telescopes. Studying these dark comets is like having a laboratory specimen of the Oumuamua mystery. If we can confirm that water outgassing is their engine, it strongly suggests that Oumuamua, too, could have been propelled by a similar, invisible release of gas, perhaps hydrogen or nitrogen, from its interior. It moves the conversation from, is this alien technology, to what specific type of natural ice could cause this effect. The discovery of dark comets transforms a singular enigma into a potential new category of solar system object, blurring the line between asteroids and comets and proving that the cosmos often hides its most interesting processes just beneath the surface. But the most definitive signal of all would be written not in light or motion, but in the very atoms of the object itself. Signal 12 is the isotopic ratio, a galactic fingerprint locked in the core of every molecule. Imagine you could hold a single grain of dust from Borisov or Oumuamua and split it down to its atomic heart. You would find that not all atoms of the same element are identical. Take oxygen. Most oxygen atoms have 8 protons and 8 neutrons, but a tiny fraction have 8 protons and 10 neutrons. This heavier version is an isotope. The precise ratio of heavy oxygen to light oxygen in a rock is a cosmic birth certificate. It is determined by the specific conditions inside the star that forged those atoms, and it is frozen in time when the object forms. Measuring the isotopic ratios of oxygen, hydrogen, or nitrogen in an interstellar visitor would be the ultimate signal, a direct numerical code telling us the exact stellar recipe of its home system. This ratio is unaffected by the object's journey. It does not change with heat or collision. It is a pristine record. Finding a ratio wildly different from anything in our solar system would be a staggering revelation. It would prove beyond any doubt that the object was forged in a stellar environment with a different fusion history, perhaps a star that was older, younger, more massive, or of a different type than our Sun. We would be holding a piece of alien nucleosynthesis, the very process by which stars create the elements of the universe. The technological challenge, however, is monumental. An interstellar object screams past us at tens of kilometers per second. To intercept it, grab a physical sample, and return it to Earth for laboratory analysis is a feat of engineering we are only beginning to contemplate. It would require a spacecraft prepositioned in deep space, waiting in ambush, and capable of incredible speed and precision. Yet, missions like this are now in active planning stages by space agencies. They are the ultimate decoders, designed not just to look but to touch and taste. The data from such a sample would not just solve the mystery of one object, it would open a window into the fundamental chemical diversity of our galaxy. It would tell us if our solar system's isotopic blend is common or rare, giving us our first true context for our own cosmic origins. This signal, still locked away, represents the future of interstellar exploration, a future where we don't just observe the whispers from the dark, but catch them in our hands and listen to the story written in their atomic bones. The atomic fingerprints we seek may be hidden within a far more subtle collective signal. If interstellar objects are as common as some theories suggest, their combined presence might bend the very fabric of space around us in a detectable way. This is the gravitational microlensing hint, a whisper of mass inferred not from light but from its distortion. Picture the gravity of any massive object, even a dark, invisible one, acting like a lens. As it drifts silently in front of a distant background star, its gravity briefly warps and focuses the star's light, causing a precise, predictable brightening that lasts for days or weeks before fading away. It is a fleeting cosmic alignment, a temporary magnifying glass held up by a passing shadow. We already use this technique to find planets around distant stars and even rogue planets drifting alone in the dark. But now, astronomers are turning this tool inward toward a potential population of smaller, closer objects. The European Space Agency's Gaia mission, which is mapping 1 billion stars with unprecedented precision, is perfectly poised to hunt for this signal. As Gaia stares at the same stars for years, it could catch the telltale, symmetric brightening caused by a small, dark interstellar asteroid passing through our galactic neighborhood. A single detection would be thrilling, but the real revolution would be statistical. If surveys like Gaia find these microlensing events at a higher rate than expected, it would be a profound revelation. It would mean the space between stars is not an empty highway, but a crowded sea of dark wanderers. These objects would be too small and too faint to see directly, yet their collective gravity would announce their presence. This would force us to completely redraw our mental map of the galaxy. Our solar system would not be an isolated island sailing through a void, but a ship navigating a dense, invisible archipelago of cosmic debris. The infrastructure of the galaxy itself would be far richer and more cluttered than we ever imagined, filled with the silent, dark remnants of countless other planetary systems. The object's heat told its own story, a quiet signal in the infrared that refused to match our expectations. When astronomers measured Oumuamua's temperature, they combined that data with its visible brightness to deduce a property called albedo, essentially how shiny or dark its surface was. The numbers did not add up neatly. The thermal emission suggested an object that was either surprisingly reflective or possessed a surface texture that managed heat in a bizarre way. This was Signal 14, an unexplained thermal whisper that further constrained what this visitor could possibly be made of. One interpretation pointed to a high albedo, meaning Oumuamua could have been covered in a shiny, metallic surface. Picture polished aluminum tumbling through space, efficiently reflecting sunlight and therefore staying cooler than a dark, heat-absorbing rock. Such a surface would align with the radar ping we never got, hinting at that dense planetary core fragment. Yet there was another, stranger possibility. The thermal data could also be explained if the object had an extraordinarily rough, porous, or fractal-like texture. Imagine not a solid wall, but a labyrinth of tiny cavities and tunnels, like a cosmic pumice stone or a layer of incredibly fine, insulating dust. Such a structure would have a huge surface area internally, trapping heat and radiating it away very inefficiently. It would feel warm to our infrared eyes for its size, not because it was dark, but because its complex architecture held onto solar warmth like a thermal blanket. This idea dovetails with theories of a dust aggregate or a fragile fractal object, a celestial structure more fluff than stone. A surface like that would also be exceptionally dark, not shiny, yet its thermal behavior would mimic something brighter. So the infrared signal leaves us with a paradox of possibilities, a shiny metallic shard or a dark, intricate sponge, two radically different identities that both fit the same scant data. This thermal ambiguity is a perfect example of how a single, faint signal can fracture our understanding into multiple, equally plausible realities, each pointing to a universe capable of building in ways we are only beginning to fathom. The violence of a star's embrace can forge the strangest messengers. This leads us to a signal of pure cosmic destruction, one that could explain the very existence of objects like Oumuamua. It is the tidal disruption event, a cataclysm so powerful it can shatter a world and fling its pieces between the stars. Imagine a comet or a small planet on a fateful orbit, swinging too close to its parent star. The star's gravity is not a gentle pull, it is a differential force far stronger on the side of the object facing the star than on the far side. This tidal force stretches the object like taffy, overwhelming its own gravity, and rips it apart in a single, violent pass. The result is not a clean explosion, but a stream of debris, a cloud of planetary shards and molten rock. Some of that debris falls into the star, creating a brilliant, temporary flare of light. But the rest, the outermost fragments, can be whipped around like a slingshot and ejected at incredible speeds, sent hurtling into the dark with enough velocity to escape their star's gravity forever. Oumuamua, with its strange elongated shape, fits this story perfectly. It could be one such shard, a splinter from a shattered alien planetesimal, stretched and spun by stellar forces before being cast adrift. Its tumbling motion and lack of outgassing could be the scars of that traumatic birth, a fragment with any surface ices completely baked off in the stellar furnace. This theory connects our local mystery to a distant, observable signal. Modern telescopes are now catching these tidal disruption events in other galaxies. They see a star suddenly flare to incredible brightness as it consumes the debris of a torn-apart world, a signature spike of light across multiple wavelengths that can last for months. Each such flash is a beacon announcing the creation of countless interstellar fragments. If these events are common, then the galaxy must be filled with the debris of destroyed worlds, a vast sea of planetary shards sailing the void. So when we detect a strange object passing through our own system, we might be witnessing the aftermath of a cataclysm that occurred billions of years ago around a star we may never identify. The visitor is not just a rock, it is a relic of stellar violence, a silent refugee carrying the story of its own annihilation in its shape and speed. This journey from stellar violence to the birth of wanderers leads us to the most profound signal of all, one that asks if these silent travelers are more than just rocks and ice. Signal 16 is the panspermia vector, the possibility that interstellar objects are not merely geological samples but biological couriers. The theory of panspermia suggests life itself could be a cosmic traveler with its basic ingredients or even dormant spores, hitching rides on asteroids and comets to seed new worlds. An interstellar object having wandered for millions of years between stars could be the ultimate ark. The unexplained signal we would search for is not a radio transmission, but a chemical one written in the language of carbon. We would look for a specific, telltale signature in the object's chemistry that hints at biology. In our labs, we know that many organic molecules, the building blocks of life, can form through completely non-biological abiotic processes in space. Amino acids, for instance, have been found on meteorites, so finding them alone is not the signal. The clue would be in their arrangement. Life on Earth shows a strong preference, using almost exclusively left-handed amino acids and right-handed sugars. It is a specific, lopsided selection. If we were to find a similar, overwhelming bias in the organic molecules on an interstellar object, a chiral purity that mirrors our own, it would be a thunderous revelation. It would suggest these molecules were not just forged in random chemical reactions, but processed or selected by a biological system somewhere else in the galaxy. It would be a fossilized fingerprint of alien life, preserved in the deep freeze of an interstellar journey. Another potential biosignature could be complex molecular patterns, like long chains of lipids or particular ratios of isotopes within organic compounds that are extremely difficult to produce without the catalytic help of biology. Discovering such a pattern on a rock from another star would be the closest thing to a message we could hope for, a signal that says life is not a rare accident on one lucky planet, but a fundamental, widespread process of the universe. This transforms every dark, fast-moving visitor from a geological curiosity into a potential time capsule. That tumbling, elongated shape speeding past the sun might not just be a shard of a broken world. It could be a library carrying the blueprints for life across the unimaginable distances between stars. It is the ultimate unexplained signal because it asks the oldest question in a new way: is life a local story or a galactic epic written one molecule at a time on the backs of these silent, wandering stones? The search for a common origin leads us to the quiet mathematics of motion. Signal 17 is not about a single object, but a potential pattern hidden within their paths, a statistical whisper known as orbital clustering. Imagine plotting the trajectories of every suspected interstellar visitor on a star chart, tracing their routes backward through the galaxy. A handful of researchers have pointed out that some of these paths appear to converge, not at a specific star, but at a single point in space and time in the distant past. The suggestion is that these objects might not be random, independent wanderers, but a family, a cluster of siblings flung from the same catastrophic event. This would be a staggering revelation. It would imply a single, violent occurrence like a stellar flyby or a planetary collision in another system, acted as a cosmic shotgun, firing a spray of debris in roughly the same direction, with some fragments eventually finding their way to us. The statistical signal is subtle, a question of probabilities. Is it more likely that we just happen to see a few objects from a single, dramatic ejection event, or that we are mistakenly connecting dots in a sky filled with random trajectories? The debate is fierce and fundamental to how science separates true signal from illusion. Astronomers call this the problem of selection bias. Our ability to detect these faint, fast-moving objects is not uniform across the sky. It depends on the power of our telescopes, the time of night we look, and even the season. We are effectively fishing with a net that has holes of specific sizes and shapes. Could it be that the apparent cluster of orbits simply traces the shape of our net, the regions of the sky we have searched most thoroughly, rather than a real family of objects? It is a classic scientific cautionary tale. The human brain is a pattern recognition machine, wired to find faces in clouds and meaning in static. This meta-signal forces us to confront our own methods. Proving a common origin would require not just a few suggestive paths, but a statistically robust sample, a number of objects so large that the odds of them clustering by pure chance become vanishingly small. We are not there yet. The data remains sparse, the sample tiny. Each new interstellar detection, however, adds another crucial data point to this statistical puzzle. Future surveys like the Vera C. Rubin Observatory promise to discover dozens or even hundreds of these visitors, finally giving us the numbers needed to settle the argument. Until then, the orbital clustering anomaly stands as a tantalizing maybe, a ghost of a pattern that challenges us to be better observers, to refine our nets and question our own assumptions about the randomness of the dark. A truly intelligent probe would not want to scream past its target. It would want to stay. This leads us to the most calculated signal of all, the hypothetical deceleration maneuver of an alien probe. Picture a civilization that dispatches a fleet of tiny, lightweight scouts across the galaxy. To conserve precious fuel, they might use the star itself as a brake. As such a probe approached a new solar system, it could deploy a vast, ultra-thin magnetic sail. This is not a cloth catching sunlight, but a web of superconducting wires generating a magnetic field miles wide. Plunging into the star's magnetosphere and solar wind, this magnetic bubble would create immense drag, gently slowing the craft down so it could be captured into orbit for a long, detailed survey. The process would not be silent. The interaction between a powerful magnetic sail and a star's charged particle wind would be spectacularly violent. It would generate a massive shockwave in the plasma, a turbulent bubble of superheated, glowing particles. Our telescopes might detect this as a sudden, localized burst of synchrotron radiation, a specific type of high-energy radio emission given off when electrons are whipped around magnetic field lines at nearly the speed of light. For a brief period, this braking maneuver could outshine the star itself in certain radio frequencies, a brilliant, unnatural flare announcing an arrival. So why have we never seen such a flash? The silence is part of the story. Perhaps such probes are incredibly rare, and none have aimed our way in the millennia we have been watching the skies. Maybe the technology uses a different, stealthier method we cannot yet conceive. Or the most haunting possibility, the maneuver happens only once when the probe first arrives. If a scout braked at our sun 1 million years ago and settled into a quiet, dormant orbit in the outer solar system, the flash of its arrival would be a fossilized event, a single page torn from a history book we were not here to read. This turns the absence of a signal into a powerful narrative device. We are not just listening for active transmissions, we are scanning the skies for the archaeological remnants of a one-time technological event, a signature that would have been as brilliant as it was brief and is now lost to deep time. It asks us to consider that the most definitive evidence of another intelligence might not be a repeating beacon, but the ghost of a single ancient engine burn forever faded from view. The night sky holds flashes too brief for most telescopes to catch. Signal 19 comes from the sharp eyes of dedicated amateur astronomers who sometimes report transient brightness spikes from fast-moving objects. These are not the smooth curves of a rotating asteroid, but sudden, needle-sharp flares that appear and vanish in seconds. Imagine watching a distant airplane and for one instant, a window catches the setting sun and flashes like a star. That is the kind of event these observers describe, a momentary brilliance against the dark. For an interstellar visitor, such a spike could be a crucial clue. One explanation is a sun glint. If the object has a flat, mirror-like panel on its surface, perhaps a cleavage face of shiny mineral or even a manufactured surface, the geometry of its tumble could align that panel perfectly with the sun and Earth for just a second, creating a dazzling, focused reflection. Another possibility is more volatile. A pocket of trapped gas beneath the surface, heated to a critical point, could rupture in a tiny, jet-like explosion, throwing a brief cloud of reflective dust into space before it dissipates. Even a collision with a speck of interstellar dust, a grain smaller than a sand, could vaporize on impact and create a minuscule, bright plasma flash. The challenge is monumental. These events are unpredictable and last less than a blink in cosmic terms. By the time a report is made, the moment is gone, impossible to verify with a second instrument. They live in the realm of tantalizing anecdote, often dismissed as equipment glitches or atmospheric interference. Yet their value is undeniable. Each unverified report is a shout for better eyes on the sky. They push us toward a future of continuous, automated all-sky monitors, vast arrays of cameras and sensors watching every patch of darkness, waiting to catch the next elusive flash. They remind us that some of the universe's most interesting signals are not steady beacons, but fleeting winks, there and gone before we can even be sure of what we saw. Every journey leaves a mark, and an interstellar voyage etches its story directly into the stone. Signal 20 is the galactic cosmic ray weathering signal, a permanent record written by deep time itself. These objects do not sail through empty space. They traverse a sea of invisible, high-energy radiation, atomic nuclei accelerated to nearly the speed of light by distant supernova and black holes. For millions, perhaps billions of years, this relentless barrage of galactic cosmic rays bombards the surface of an interstellar wanderer. Each impact is a tiny nuclear event, shattering atoms in the rock and creating rare, exotic isotopes that do not form under normal planetary conditions. It is a slow, invisible alchemy transforming the very chemistry of the surface layer. This process creates a unique fingerprint, a cosmic ray exposure age. By measuring the concentration of specific isotopes, like certain forms of neon or helium, scientists can essentially read the clock, determining how long that surface has been exposed to the harsh environment of interstellar space. For an object born in our solar system, that clock would read no more than about 4.5 billion years, but for a true interstellar traveler, the clock could tick far longer. Finding an object with a cosmic ray exposure age older than our solar system would be a definitive, unshakable signal. It would be a geological passport stamp proving an origin beyond our sun. We could detect this signal in two ways. The first is through incredibly detailed, close-up spectroscopy. If we could get a spacecraft alongside the object, its instruments might detect the subtle spectral signature of those radiation-altered minerals, a faint whisper of atomic change. The second, more certain method is a physical sample return. Bringing even a gram of that weathered crust back to Earth would allow us to count the atoms of those rare isotopes in a lab, telling us not just that the journey was long, but precisely how long. The weathered surface becomes a logbook. A thick, heavily altered crust suggests an ancient, slow journey through the galactic disk. A thinner layer might hint at a younger object, or one that took a quicker path through less dense regions of cosmic rays. This signal turns the object from a mere rock into a veteran of the void, its face bearing the scars of an epic pilgrimage across light years, a silent testament to the enduring, transformative power of the galaxy itself. That weathering crust tells us a journey's age, but it cannot tell us where a traveler might decide to stay. Our solar system possesses its own quiet, gravitational parking spaces, places where an object can remain for eons, held in a delicate balance between worlds. These are the Lagrange points, and they may be hiding our next unexplained signal. The hypothesis is simple yet profound. What if some interstellar visitors did not just fly by? What if they were captured? As a fast-moving object from another star tears through our solar system, the complex gravitational dance with the Sun and a giant planet like Jupiter could, under perfect conditions, slow it down just enough to snare it into a stable orbit. The most likely holding cells are the Earth-Sun Lagrange points, specifically L4 and L5. These are points 60 degrees ahead of and behind Earth in its orbit, gravitational valleys where an object can park almost indefinitely. Finding a captured interstellar object lurking in one of these points would be Signal 21, a discovery of monumental importance. It would mean our solar system is not just a way station for passing rocks, it is a collector. For billions of years, we may have been gathering samples from other stars, tucking them away in these cosmic cubbyholes, creating a silent museum of galactic geology right in our own neighborhood. But how would we find such a lonesome, dark rock against the crowded starfield? The signal would be incredibly faint. We would search for it in two ways. First, by its reflected sunlight. Even a dark object reflects a tiny amount of light, and a dedicated survey scanning the Lagrange regions could pick up a moving point of light that does not match any known asteroid. Second, and perhaps more promising, is its thermal glow. Every object in space, no matter how dark, emits a faint heat signature in the infrared. A cold, captured wanderer would glow with the residual heat it has slowly absorbed from the distant sun. Telescopes like NASA's upcoming NEO Surveyor, designed to hunt for near-Earth objects, could potentially detect this whisper of warmth against the cold backdrop of space. Finding one of these Lagrange point lurkers would change everything. Instead of launching a frantic, years-long mission to chase a fleeting visitor screaming past at incredible speeds, we could send a spacecraft on a relatively short, calm journey to a parked specimen. We could study it up close, map its surface, and perhaps even retrieve a sample with comparative ease. It would be a pristine time capsule from another star, delivered to our doorstep and waiting patiently for us to open it. This transforms the search from a race against time to a deliberate archaeological dig in our own celestial attic. The dark, quiet points of balance in our solar system may hold the greatest treasures of all, silent prisoners of gravity that carry the untold stories of the galaxy. Light itself can carry hidden messages in its very orientation. When sunlight bounces off a surface in space, the scattered light waves often become polarized, meaning they vibrate more strongly in one particular direction. This polarization is a powerful forensic tool. By measuring it, astronomers can infer incredible details about an object's surface without ever touching it. A smooth, metallic surface polarizes light in one distinct pattern. A rough, dusty regolith scatters it differently. It is like looking at the world through a pair of polarized sunglasses that can reveal texture, composition, and even structure. For our first interstellar visitor, this offered a chance to finally read its surface. Based on Oumuamua's extreme shape and its mysterious acceleration, scientists calculated what its polarization signature should look like. The predictions were clear, yet when telescopes measured the actual polarized light coming from the tumbling object, the data did not match. This subtle but critical discrepancy is signal 22, the polarization mystery. It tells us in the quiet language of physics that our best models of what Oumuamua is made of are still incomplete. The light was polarized, but not in the way a simple, homogeneous surface should produce. One compelling explanation is that the surface is not uniform. It could be covered in a layer of porous, fractal-like dust, a fine, insulating fuzz that scatters light in incredibly complex ways. Picture the difference between light reflecting off a flat mirror versus light bouncing around inside a pile of crushed velvet. The velvet's intricate structure would create a polarization signature full of subtle twists that simple models cannot yet capture. Another possibility is that the surface is layered like a cosmic onion, with different materials or densities beneath a thin crust. Sunlight penetrating a translucent layer of ice or a porous matrix before reflecting back out would carry a mixed signal, a blend of polarizations that tells a confusing story. This mismatch is not a failure of science, but its engine. It forces us to invent new models, to consider materials and structures we have not yet catalogued from our own solar system. That faint, polarized glint was a whisper from an alien geology, a direct message that the surfaces of other worlds are fashioned by processes we are only beginning to understand. Borisov's light told a story of both presence and absence. While its spectral lines blazed with cyanogen, they held a puzzling silence where other common gases should have been. This is signal 23, the volatile depletion puzzle, a chemical whisper about what was missing. In our own solar system, comets are rich in volatile compounds, lightweight gases that vaporize easily. Carbon monoxide and carbon dioxide are two of the most abundant. They are the first to boil away when a comet warms, creating the spectacular comas and tails we see. Yet Borisov, despite its obvious activity and brilliant tail, showed a severe shortage of these particular ingredients. Its chemical recipe was strangely lopsided. This selective depletion is a direct clue, a forensic trace left by the object's history. One possibility points to a birthplace of extreme cold. If Borisov formed in the outermost, frigid fringes of its protoplanetary disk, where temperatures were just a few degrees above absolute zero, the chemistry would have been different. In that profound chill, certain molecules like carbon monoxide might have remained frozen onto dust grains in a different proportion, or perhaps they were less abundant in that region of the disk from the very beginning. The comet would then be built from a local inventory that simply lacked these common volatiles. The other leading explanation involves a later chapter in its life. Perhaps Borisov did form with a normal complement of carbon monoxide and dioxide, but sometime after its birth, it experienced a warming event. This could have been a gentle, long-term drift inward toward its home star, or a sudden gravitational kick that sent it on a closer orbit. That heat would have acted like a slow cooker, preferentially baking away the lightest, most volatile gases first, leaving behind a depleted crust over a still icy interior. When it was finally ejected into interstellar space, it carried this altered chemical signature with it. Think of it like a sponge. If you leave a wet sponge out in the sun, the lightest water molecules evaporate first, leaving the heavier moisture behind. Borisov may be that partially dried sponge, telling us a story not just of its formation, but of a thermal history we can only infer. This puzzle transforms a simple chemical list into a geological timeline. The depletion pattern is a signal etched by either the deep cold of its cradle or the subtle warmth of its adolescence, a permanent record of the environmental conditions in an alien planetary nursery we will never see directly. It reminds us that every object is an archive, and sometimes the loudest messages are written in the things that are no longer there. Rotation itself can be a message, a steady rhythm in the dark. For Oumuamua, the chaotic tumble we observed might have been just the final chapter of a much longer story. Some computer models analyzing its complex motion suggested a fascinating possibility. They hinted that Oumuamua could have been in or was transitioning into a state of synchronous rotation. This is signal 24, a hidden cadence in its spin. You see this with our own moon, which is locked in synchronous rotation with Earth, always showing us the same face because its rotation period matches its orbital period. For an interstellar object, achieving such a lock is a profound clue. It does not happen by accident. Synchronous rotation is typically the result of tidal forces, a gravitational tug of war that over millions of years slows and aligns a smaller body's spin to match its orbit around a much larger one. For Oumuamua to be in such a state, or even approaching it, implies a past of remarkable intimacy. It suggests that long before its journey to us, this object spent an immense amount of time orbiting something. Perhaps it was a moon of a giant planet in its home system, its spin gradually braked by the planet's gravity until one face was permanently turned toward its captor. Or more dramatically, it could have had an extremely close encounter with its home star, a grazing pass that exerted tremendous tidal friction, violently reshaping it and altering its spin in a single catastrophic event. This rotational signal would rewrite the object's thermal history. If one hemisphere was constantly facing a heat source for eons, that side would have been thoroughly baked, its volatile ices completely driven off, while the far side remained in perpetual shadow, potentially preserving primordial ices. This could explain the lack of a visible coma. The side facing the sun during its passage by us might have been this ancient, baked crust, utterly depleted and inactive, while any remaining volatiles were trapped on the permanently dark side, unable to vent. The light curve we saw, that wild, tumbling brightness, might then be the signature of an object recently knocked out of its stable, locked state, sent wobbling chaotically after being gravitationally ejected from its home system. While this synchronous rotation is only a speculative model, not a confirmed observation, it adds a breathtaking layer of narrative depth. It transforms Oumuamua from a simple wanderer into an object with a rich and violent biography, a celestial body that was once part of a system, bound by gravity to a planet or star before being ripped away and sentenced to an eternal, solitary voyage. Its spin holds the ghost of a past attachment, a silent rhythm that speaks of a home it left behind billions of years ago. The final signal is not a whisper from the past, but a roar from the future. We stand on the brink of a revolution in our understanding, not because of a single, brilliant anomaly, but because of an impending flood of data, the Vera C. Rubin Observatory's legacy survey of space and time will soon begin its epic watch, scanning the entire southern sky every few nights with a camera the size of a small car. Its power is almost incomprehensible. Where we have found 2 interstellar visitors in a decade, the LSST is expected to find dozens every single year. This coming deluge of discoveries is itself the 25th, and perhaps most important, unexplained signal. It is the promise of a statistical universe, a shift from puzzling over rare, singular curiosities to mapping an entire population of interstellar wanderers. For the first time, we will move from asking what is this one strange thing to asking what are they like as a class. Within that flood, we will almost certainly find signatures that make Oumuamua and Borisov look ordinary. We may find objects on trajectories so hyperbolic, so fast, that their origin points to a dramatic event like a supernova explosion, rather than a gentle ejection from a planetary system. We will capture the light of dozens of these passers-by, building a library of spectral fingerprints. In that library, we may find an entirely new spectral type, a chemical signature that does not match any known asteroid or comet, pointing to a formation environment utterly alien to our own. Or we might see a pattern that chills the blood. Imagine the LSST detects a cluster of a dozen objects, all moving in a tight formation, on parallel paths from the same point of origin. Such a synchronized arrival would be virtually impossible under natural models of ejection. It would look less like a random spray of debris and more like a fleet. The sheer volume of data will allow us to finally answer the haunting questions that have lingered since that first tumbling shape. Is the extreme elongation of Oumuamua a freak accident or a common architectural feature of interstellar fragments? Is Borisov's chemical purity the rule or the exception? The mysteries will not end. They will deepen and diversify, but they will be grounded in a new reality of numbers and probabilities. We will trade tantalizing anecdotes for hard statistics, transforming lonely whispers into a chorus of cosmic voices, each with its own story to tell. The greatest signal of all is the one that tells us we are no longer just watching the dark. We are beginning to listen to its true conversation. These faint whispers from the dark do not announce themselves. They must be hunted, captured from an ocean of cosmic noise by the most ingenious machines humanity has ever built. The search begins with the great optical sentinels, telescopes like Pan-STARRS in Hawaii and the Catalina Sky Survey in Arizona. Night after night, they methodically photograph the same swaths of sky, comparing images to find the tiniest speck of light that has moved against the fixed background of stars. That single, shifting pixel is the first clue, a digital whisper of motion in a static universe. But one image is not enough. The hunt requires a chain of observations, a trail of breadcrumbs across the nights, to calculate an orbit and confirm the object is not just another asteroid from our own backyard, but a true interstellar traveler screaming through on a hyperbolic path. This visual chase is a race against time and celestial mechanics, a frantic effort to pin down the target before it vanishes into the depths. Once a candidate is identified, the call goes out across the global network of astronomy. The world's most powerful eyes turn to look. Giant radio dishes like those in the Very Large Array or the Allen Telescope Array listen not for reflected sunlight but for the object's own emissions. They tune across millions of frequencies, straining to hear the faint hum of a natural radio source or, against all odds, the structured pattern of an artificial transmission. Simultaneously, optical and infrared telescopes, from the Hubble Space Telescope to the mighty Keck observatories on Mauna Kea, perform a kind of cosmic chemistry. They break the object's faint glimmer into a spectrum, spreading its light like a rainbow to read the chemical signatures within. Each of these instruments is a specialized translator, built to interpret one specific dialect of the universe's physical language. The raw data from these telescopes is a flood of chaos. It contains the hiss of the universe's background radiation, the glare of nearby stars, the electronic noise of the instruments themselves, and the distortions of our own atmosphere. Finding the true signal within this petabytes of noise is the next monumental task. This is where the data processing pipelines come in, the silent, algorithmic brains of the operation. Sophisticated software filters out the known interference, aligns thousands of images, and flags anything that moves or shines in an unexpected way. It is a digital sieve designed to catch the one in a billion anomaly that might be our next interstellar visitor. These pipelines are the unsung heroes, the tireless librarians sifting through a universe of static to find the one page with a new story. Knowing we cannot rely on luck alone, we are building the next generation of hunters. The European Space Agency's Comet Interceptor mission represents a revolutionary shift in strategy. Instead of chasing an object after discovery, it will launch and then wait, parked in a gravitational holding pattern at a Lagrange point, ready to spring into action the moment a pristine interstellar comet or a new visitor is identified. It is a cosmic ambush predator poised for the perfect opportunity. Its suite of instruments will do what we could not do for Oumuamua. It will fly alongside the visitor, mapping its surface in high resolution, sniffing its coma with mass spectrometers, and measuring its magnetic field. It will transform a fleeting point of light into a detailed, three-dimensional world. Beyond ready response missions, scientists are now designing probes dedicated solely to intercepting interstellar objects. These concepts involve advanced propulsion, like solar sails or next-generation ion engines, to achieve the incredible speeds needed to rendezvous with a target moving at dozens of kilometers per second. They would carry not just cameras but drills and sample return capsules. The goal is no longer just to observe but to touch, to bring a piece of another star system back to Earth for laboratory analysis. These future missions represent our commitment to moving from passive observation to active interrogation. We are no longer content to watch the mysterious travelers pass by our window. We are building the tools to run outside, flag them down, and ask them directly where they came from and what they are made of. The greatest signal we are preparing for is the one that comes from our own ingenuity, a message to the cosmos that we are finally ready to listen, not just with our ears but with our hands. The galaxy is not a collection of isolated islands, but a vast, churning sea of shared stories. Each of these 25 unexplained signals, from the silent push of Oumuamua to the pristine chemistry of Borisov, is a single sentence in a much longer message. Together, they tell us that interstellar asteroids and comets are not mere curiosities. They are the galaxy's primary messengers, carrying news across the light years about birth, death, and everything in between. They are the connective tissue of the Milky Way. When we study these visitors, we are reading a cosmic postal system, where every rock is a letter stamped by the conditions of its home star. The chemical fingerprints tell us about the diversity of planetary kitchens. The strange shapes and tumbling spins narrate tales of gravitational violence, of worlds shattered and flung into the dark. The missing gases and thermal whispers hint at hidden structures and forgotten climates around alien suns. Even the radio silence and the absence of visible tails are data points, telling us what is not there, which is often just as revealing as what is. This changes our fundamental picture of the universe. It suggests that materials are constantly being exchanged between star systems. A planet forming around a young star might incorporate dust grains that once belonged to a comet from a completely different stellar nursery. The ingredients for life, the water and organics, could be galactic travelers, hitching rides on these dark wanderers to seed new worlds with potential. This makes the galaxy profoundly interconnected. Your glass of water might contain hydrogen atoms that once ice a comet in another system billions of years ago. The unanswered questions these signals raise are the most valuable part. They force us to confront the limits of our knowledge. Is Oumuamua's shape a common feature of interstellar shrapnel, or a bizarre one-off? Is the absence of certain chemicals in Borisov the rule for other systems, or an exception? Each mystery is a piece of a grander puzzle, the puzzle of how common planets like Earth truly are. If the galaxy is teeming with these messengers, and if they carry such a wild variety of materials and histories, then the processes that build planets must be happening everywhere in countless variations. It means solar systems are not static museums, but dynamic, evolving entities that constantly lose and gain material. A quiet, stable system like ours might periodically be peppered with fragments from a catastrophic collision around a neighboring star, delivering new elements and maybe, just maybe, the spark of something more. The ultimate signal from all this noise is one of cosmic humility and breathtaking possibility. We are not separate observers of a distant universe. We are participants in a flowing, material exchange that spans the entire galaxy. Every unexplained flash, every silent acceleration, is a clue in the greatest detective story of all, the story of how we came to be here and who or what else might be out there reading the same messages written on the stones of the void. So we have followed these whispers across the light years, from the silent push of Oumuamua to the pristine chemistry of Borisov, from the ghost of a radio burst to the promise of a hidden fleet. These 25 unexplained signals are not a catalogue of failures, but a map of the frontiers of human curiosity. Each anomaly, each puzzling silence, is a question the universe has asked us directly, and science thrives on such questions. They are the engine of discovery, pushing us to build better telescopes, design smarter missions, and challenge our most comfortable assumptions about how the cosmos works. The mystery is the point. It means there is still so much more to learn, and that is the most exciting place to be. This story does not end here, it is accelerating. The Vera C. Rubin Observatory will soon begin its watch, and the James Webb Space Telescope peers deeper into cosmic chemistry than ever before. Your curiosity is part of this journey. Stay tuned to these missions, for the next interstellar visitor could be spotted tomorrow, carrying with it a brand new riddle written in light and motion. We want to hear from you. Look back through these 25 signals. Which one captures your imagination the most? Is it the eerie, repeating radar pattern we never heard, or the biological time capsule of the panspermia vector? Share your thoughts and theories in the comments below. The greatest signal of all may be the one we create together, a shared sense of wonder as we stare into the dark and listen for the next whisper from the stars.